Hi, today we will discuss about an important and easy shortcut how to solve unbalanced Wheatstone bits. Before going to the unbalanced Wheatstone bits, I will move to a brief idea about what is balanced Wheatstone bits. In the balanced Wheatstone bits, the five resistors are here. Now this is R1, now this is R2. Now this is R3, this is R4. This junction is connected by another resistor R5. If the ratio between adjacent resistors, that is R1 by R2 equals to R3 by R4. The ratio between adjacent resistors are equal. Now this intermediate resistance does not work. So that is nothing but, let us take an otherwise R1 by R3, R2 by R4. That is ratio between any two adjacent resistors is equal. Then the resistor which is in between this junction is not working. Means there is no current passing through this. So let us go to the simple example here. The two resistors are there. So the four resistors are there. This is look at here. Now this is a 5 ohm. Now this is a 10 ohm. Now this is a 10 ohm. Now this is a 20 ohm, which is connected with this is a 5 ohm resistor. So once look at here, the ratio between these two resistors 5 and 10 is 1:2, 10 is 20 is 1:2. So this is exactly the condition for the balanced Wheatstone bits. Now this 5 ohm resistor is not work here. Now these two are in the series combination, these two are in the series combination. Now the 5 and 10 is, the resistor becomes 15. Now the 10 and 20, the resistance becomes 30 ohm. Now the both are in the parallel. When these two are in the parallel, so just go directly R1 R2 by R1 plus R2. Now this equivalent is equals to 15 into 30 by 45. 15 1 15 3 that should be equals to 10 ohm. This is easy to solve the balanced Wheatstone bits. Suppose now I will write down an unbalanced Wheatstone bits by changing the positions of the resistances. Look at here. By changing the positions of the resistances, I will write this is now this is a 5 ohm, now this is a 10 ohm, now this is a 20 ohm, this is a 10 ohm, this is connected by 5 ohm. Look at here, these two resistors, this is 5:10 is 1:2, this is a 2:1. This is not the case for the balanced Wheatstone bits. Now how to solve these balanced Wheatstone bits problems? There is a two important shortcuts are there. One is delta to star transformation and star to delta transformation. So what is delta to star transformation? Let us take that three resistors are in the form of a delta. Now this is R1, now this is R2, this is R3. Now this combination of 1 and 2 one resistor, this combination of 1 and 3 another resistor, the combination of 2 and 3 is another resistor. That means the resultant of the two adjacent sides of the delta gives one resistor. That gives us like here. Now this is combination of 1 and 3, this is R13. This combination of 1 and 2, this is R12. This combination of 2 and 3, R23. So again, so we have to that. So how to write it? R12 and R13 and R23. Just look at here. Then R12. So R12 is the combination, the equivalent resistance of 1 and 2. This is the product of, look at it, the product of the two sides of the delta and find the sum of all the resistors. Now look at here, R1 into R2 by R1 plus R2 plus R3. Now look at here, R13 equals to R1 into R3 by R1 plus R2 plus R3, and R23 is equals to R2 into R3 by R1 plus R2 plus R3. So now this part of the circuit, look at this part of the circuit in the form of this delta. So just I rewrite this circuit here. Look at this. Now this is a 5 ohm, this is a 20 ohm. Now this is a 5 ohm. Now this is a 5 ohm, this is a 20 ohm. Now this is a 5 ohm. Now this is another resistance 10 ohm here. Another arm. Now this is a 10 ohm. So now we have to find the equivalent resistance between those two. So look at here. So what you have to do? This is, I will take this is a R1. Now this is a R2. Now this is R3. Now the combination of 1 and 2 1. The combination of 1 and 3, the combination of 2 and 3. So what is 1 and 2 combination is here? Look at here. What is 1 and 2 combination? 1 is 5 ohm, 2 is 20 ohms. Look at here. So 5 into 20 by sum of all the resistors. 5 plus 5, 10 plus 20, 30. Now that should be equals to 10 by 3 ohm. Now this 1 into 3. So 1 into 3 in the sense 5 into 5. So 5 into 5 by sum of the resistors is 3. So 30. That should be equals to 5 by 6 ohm. And the next we move to the R2 into 3. So R2 into 3 means 20 into 5. So 20 into 5 by 30. That should be equals to 10 by 3. 10 by 3 ohm. So now how this circuit becomes, look at this. So the combination of 1 and 2. Combination of 1 and 2 is 10 by 3. The resistor is 10 by 3 ohm. The combination of 1 and 3 is like here. The combination of 1 and 3 is 5 by 6 ohm. So the combination of 2 and 3, the 2 and 3 is like here. The combination of 2 and 3 is 10 by 3 ohm. So there's remaining two resistors are right like here. Now this is a 10 ohm. This is a 10 ohm. Now this is the equivalent resistance between those 2 points. So just look at the circuit. What the initial circuit is here, now it becomes more easy. They are very simple now. So what I have to do? So these two are in the series combination. Now these two are in the series combination. Then effective resistors are in parallel. Then the equivalent with this is series combination. Now I have to write that what is the series combination of 5 by 6 and 10. So 5 by 6 plus 10, that should be equals to 65 by 6. Now this is 10 by 3 and 10 series. That is a 10 by 3 plus 10. That should be equals to 40 by 3 ohm. So now these two are in the parallel. So these two are in the parallel. So these two are in the parallel in the sense the 1 by R equivalent is equals to 6 by 65 plus 3 by 40. 6 by 65 plus 3 by 40 is equals to, that is a 240 plus 3 5 is a 15, 3 6 is a 18 plus 1, 90, 195 by 65 into 40. Now this 240 plus 195 is like here. There is a 5, this is a 13, 2 plus 1 is 3 plus 1, 435 by 65 into 40. So 513 ja, 587 ja. Now this is 87 by 520. This is 1 by R equivalent. So therefore, then R equivalent of this equals to 520 by 87. So this is the equivalent of this, all the combination is equals to 520 by 87 ohm. So now these two are in the series. Now this circuit becomes, this is 10 by 3. This is 520 by 87. Now these two are in the series. So here very clear series in the sense R1 plus R2. Now this equivalent resistance, what is requirement is 10 by 3 plus 520 by 87. So the 87 and the 9, 329 is 87. So what I am doing here, multiply with 29 the numerator and the denominator. So that should be equals to 290 plus 520 by 87. So now this is equals to 0, 1, 5 plus 2, 1, 7, 7 plus 1 is 8, 8, 10 by 87. This is close to that, it's not 10 exactly, it's close to in between 9 and 10. So 9 7 is 63, 9 8 is 54 plus 6 is, sorry, 9 7 is 87 into 9, 9 7 is 63, 7, 9 8 is 72 plus 8 is 72 plus 6 is 783. So it's close to 9, more than 9 values. So this is close to the 9.2 or 9.3 ohms approximately. So this is a easy method how to convert a formation which is an unbalanced Wheatstone bits. The sum part is in the delta formation, how to convert delta to star formation. So in the next class, we will move to the one more example as another shortcut to solve the unbalanced Wheatstone bit similar problems by using the star to delta transformation. I hope you understand this. Thank you.